Okay, so the point that I'm really trying to drive home in chapter 5 is that the integral is equal to the area under the curve. And I really want to get this idea that what we're going to do is we're going to break this up into little boxes that have a height f of x and a width dx, and so then I'm going to get dA is equal to f of x times dx. Okay, so now what I really want to do is I want to sort of I want to give you a formula, and let's say we've got a parabola y equals x squared, and I want to know this area here from 0 to 4. Okay, so what I'm going to do is I'm going to say that my change in the area is going to be x squared times dx. And now there's this whole thing called the fundamental theorem of calculus, and I'm not really sort of a big fan of it, even though it is the fundamental theorem of calculus. But here's roughly how it goes. Is you go, wait a second, I've sort of seen this before. If I had some function a, if I use implicit differentiation, on a, I'm going to get dA. Now, if I'm saying that dA is x squared dx, then what function, if I take the derivative, okay, the derivative of what function equals x squared dx? And you go, oh gosh, so my power rule, okay, so if I gotta remember my power rule, I say y equals x to the n, and so then dy is going to be nx to the n minus 1 dx. I'm starting to remember something here. And you go, oh, so what? So this means, so my power rule for derivatives is multiply by the exponent and reduce the exponent by 1. Okay, so my power rule for the derivatives is first thing I got to do is multiply by the exponent, and then I've got to reduce the exponent by 1. And then tack on a dx at the end. Okay, so now how do I do this in reverse? Well, reduce the exponent, so antiderivatives instead of reduce, so I got to work backwards. So 1 by exponent, the reduce. Let's change that into add 1 to the exponent. And then multiply by the exponent. Well, what's the opposite of that? What's the reverse of that? Then divide by the new exponent. Because this was the exponent that was on there, and then we reduced it by 1, so we're going to add 1 to it, and then we're going to divide by the new one. So what I'm going to say is, if dy equals x to the n dx, what I want to do is I want to say that y is equal to x to the n plus 1 over 1 over n plus 1. So, in other words, up here, I'm going to do, that's going to be x cubed times 1 over 3. So, this function here, when I take the derivative of this function, I get this function. Now, I need to add on that there can also be a constant added onto that, because if you take the derivative of a constant, you get 0. So, this is the antiderivative of this. So x squared dx is the derivative of 1/3 x cubed plus c. 1/3 x cubed plus c is the antiderivative of x squared dx. Okay, so that gives me this idea that I just want to keep rocking right on into this video. So I had this function. I had my dA from the spreadsheet that I was working on. Let's see if I can remember it. It was 10x squared minus x cubed over 50 dx. Okay, so this is a little bit advanced, but I think we can do it. So I'm going to rewrite this. dA equals, I'm going to write this as 1 over 5 x squared minus 1 over 50 x cubed dx. And I sort of say, okay, well, what the derivative of what gives me dA? Well, the derivative of a gives me dA. Now I just use this rule that I just sort of came up with, and I say that 1 over 5 times x to the third times 1 over 3 minus 1 over 50, and then I've got x to the fourth times 1 over 4. And so I should get that my area is equal to 1/15 x cubed minus 1 over 200 x to the fourth. Now, I want to know, where did I start? Where did I start? I started at 0 and I ended at 10. So let's see what happens if I plug 0. What happens if I plug 10 into this? If I plug 10 into this, I get 1 over 15 times 10 cubed minus 1 over 200 times 10 to the fourth. What happens if I plug 0 in? If I plug in 0, I get 1 over 15, 0 cubed, minus 1 over 200, 0 to the fourth. That's all going to equal 0. This is going to equal, well, if I just sort of do it out on my calculator, I got 10 cubed divided by 15 minus 10 to the fourth divided by 200, and I've got A equals 16.667, which is exactly what I got in the other video. So what this is saying is that that is the derivative of some function a. Okay, so let me just sort of say that the... now I just got to reintroduce some new stuff here. But basically I'm going to be done with this video in a few seconds. I'm going to say that a is the integral of f of x dx. I'm going to call this f of x, capital F of x. Okay, so this is really important. So f of x dx is the derivative of some function capital F of x, and capital F of x is the integral of f of x dx. Okay, so what does this sign mean? So basically, one more, I'll throw it up here. Okay. Okay, so this sigma, this sideways, this E as some people call it, is a Greek, capital Greek S, which is Greek sigma, and it means sum. And sum means add up all of the. So what this means, this is just an elongated S. This elongated S means add up the infinite number of infinitesimal blah, blah, blah. So I'm just going to start a new page, and I'm going to say what this is. What this means to me is this says what this says to me is add up the infinite number of boxes that have a height f of x and an infinitesimal width dx. And when you do that, you're going to get the area under the curve, which is some function f of x, capital F of x, and like I said before, capital F of x is we're going to call that the integral of f of x dx, and f of x dx is the derivative of that function capital F of x. That's a lot to digest in one video.